Recording is on.
Hi, everyone, and welcome once again to Papers We Love Seattle. Uh, I am uh, one of your hosts, Trevor Manaw. The other host is our speaker tonight, uh, Max Payton. Uh, hey, Max, how's it going? Um, a couple things before we start. As always, we are looking for people to lead discussions on papers that you love. So if you have a paper that you are interested in or are excited to talk about, please contact us. Reach out to us. We are always around in our Slack channel, which you can get to at papersweloveslack.herokuapp.com. I'll put that link in the chat here in a minute. So check us out on Slack. We're also on Twitter. We're on YouTube at youtube.com/paperswelove as well, where you can watch all of our past talks. We do have a code of conduct, which is on our GitHub. It's also on our Meetup. So please give that. We definitely take it seriously. If anyone's acting up, we might ask them to leave. If you're having any issues either during the talk or afterwards, feel free to reach out to myself or Max. Our contact information is in the code of conduct. A couple announcements. One, we're like semi looking for a location / sponsor in the Seattle area to do this live in person, because I think that would be really fun. But no traction quite yet on that. So if you have some contacts, please reach out to Max or myself, and we can see what we can do about doing this in person one of these days. We haven't done that in a while, obviously. The other announcement is Strange Loop is on and in person this year. That is going to be September 21st through the 23rd, I think. And the day before Strange Loop is Papers We Love Conf. I'll be out there volunteering. So if you want to come see me in person, go buy your tickets to Strange Loop, buy your tickets to Papers We Love Conf, and fly out to St. Louis and say hi. So I'll be there. Hope to see some of you out there too. Max, do you have any announcements, or anyone really?
Please come and give talks. We don't have anyone for next month right now.
It's true. It's true. Anyone else have any announcements before we hand it over to Max?
It's super easy to do one of these talks.
It's super easy. Max is going to show you how easy it is. All right. And with that, I'll hand it over to Max. Here you go.
All right. Let me go and share my screen. Chrome tab. Okay. Can everyone see my screen?
Yeah, it looks good.
Okay.
Yep.
So, my name is Max Payton. I'm a person who likes learning about history. I think it's really cool to not just learn what things are the way they are, but why they are the way they are, and how they got to be that way. There is a really good talk from Deconstruct Conf that I will find later, and if I was smart, I would have linked in this talk. By I can't remember his name now. He's cool, but he basically gives a talk about why it's important for even computer scientists to know the history of their own field, to understand how things got the way they are, because it's just it affects how you even what you've learned, what things have been learned over time and stuff. So I agree. I think it's important to understand the history of kind of what you do as well. And I'd be interested in giving some more talks about the history of various programming languages. There's a really interesting history of how we got to the way programming languages are itself. And I'd like to find a paper on that sometime. But that's all an aside. So I'm going to start with this chart. We'll mention this at the end, but this is a chart that kind of really is kind of one of the driving forces behind this paper, I would say. And it's kind of maps out what I think the author lists as like major developments in the history of data visualization. So data visualization. So let's keep going. So we start with pre-17th century. So we are any time before the 17th century, anytime before 1600, which is a lot amount of time. And it turns out there's not a ton of data visualization at this point. We have star maps and geographic maps. So, people are drawing maps. You've seen star charts. God, I could have had an image for this. Ptolemaic star charts. Egyptians used developed coordinate systems for planning how they were going to build towns. This paper doesn't really get into any Eastern developments. It's very focused on European and then American developments. So I do not know if there were any visualization work going on in, let's say, China or India at this time. That's an important amendment that probably I should look into. But like most Western history, it kind of ignores non-Western history. So whatever. But yeah, Egyptians used coordinate systems for planning. We've had lat long, approximate since 200 BCE. Romans and Greeks. We had spherical projections of the Earth into latitudes and longitudes as of 100 CE. Ptolemy did this. Ptolemy, great mathematician, great mathematician, astronomer, wrong about a lot of stuff. That's okay. He was early on. But yeah, but this is mostly what people are doing with maps and with plotting stars. That's stars and maps. That's it. This is an anonymous 10th century diagram of mapping celestial bodies. It's the first known use of something akin to graph paper, which is cool. It wouldn't be patented for another 500 years, but they're doing it. And it also implies an implicit notion of a coordinate system. We don't know what the coordinate system is, but there is some sort of implicit coordinate system here. Planetary movements, cyclical conditions over time by an unknown astronomer appearing in the 10th century appendix and commentaries on some book. Cicero's Insomnium Scripionis. So we have some graphs here. So we're already doing some graphs. By 14th century, Nicole Oresme, who's the bishop of Lysias, theorized plotting of a theoretical function, a proto-gar graph, and plotting values. Unfortunately, he did not actually. He said like you could probably do this. He unfortunately did not really have the data to actually do it. In the paper, the author references another historian who basically says, or mathematician, I'm not sure which one he is, both probably, who basically says if Nicole Oresme had access to data to plot, like the field of data visualization would have been advanced like 400 years. Like this guy was like so far ahead of his time with what he was talking about in this thing, and he just didn't really have anything to work with, so it kind of ended there. And Nicholas of Cusa theorized plotting distance versus speed, which we would later Newton probably maybe did. I don't know if Newton actually did any plotting, but sure, we do now all the time. And then we really wait till we get to the 16th century for anything else. Where we're starting to measure, we're trying to get accurate measurements of things. Before, we've had very approximate measurements. I looked at a shadow on the ground and I approximated the sphere, the size of the Earth. I approximated this by putting a bunch of things that I kind of know the size of. If anyone has any questions, feel free to interrupt at any time, by the way. That's fine. Otherwise, I'm just talking. So Tycho Brahe has his wall quadrant to measure celestial positions more exactly. And here is a engraving of his mural quadrant. You can see this little hole up here. Light would, when things would come through, they would measure where it fell on this quadrant thing that he had exactly built out, and he'd record these measurements. with his 2 assistants, I guess. I read a description of how this worked on Wikipedia. This is not a great engraving. The sizes seem a little off, but so it goes with Middle Ages art. We have the invention of triangulation to improve people's ability to know where they are. We have the first early photography, like the camera obscura, which was capturing sunspots. So we're starting to kind of be able to visualize things. We have we're starting to tabulate mathematical functions. George Rheticus makes trigonomic tables in 1550. And we have a cartographic atlas by the Theatrum Orbis Terrarium by Abraham Ortelius in 1570. So we're starting to measure things at this point, but we're not really doing much with them. We're making tables, we're doing measurements, we're inventing photography. So now we start getting into the 1600s, and this is where the author really starts kind of taking the history of data visualization. So to be honest, one thing I don't like about this paper is he doesn't really get into like the historical context of what was happening in the world as much, except for here, which I think is interesting because like it really helps justify like why anyone was doing this work. So in the 1600s, this is the age of sail. This is 1600 is the age of sail. It's when we start. It's when the Europeans start colonizing. We're really interested in navigation, really interested in astronomy because it's related to navigation, really interested in surveying because it's related to navigation and colonialism, really interested in territory expansion because it's related to navigation and territory expansion, and really interested in political control because at this point we're like, wait, we're starting to get like science and stuff. Like maybe we can like tax people more effectively. Maybe we can like actually know how rich we are, which we aren't really effectively able to do. So we have Descartes inventing analytical geometry. That was pretty cool. We have Fermat invents formalized coordinate systems. With Descartes, we have Galileo is starting to do error analysis on the observations of Tycho Brahe. So that's the kind of beginnings of statistics when we start saying like, could this be wrong? How much is it wrong? How good is these measurements? And then, that sounds like we're starting into statistics. Fermat and Pascal invent probability theory. They also start talking about it. John Gaunt invents demographic statistics. You've probably heard of John Gaunt. And William Petty, who I've never heard about before this paper, discusses political arithmetic for understanding the wealth of a state. He's really interested to know is how rich we are. How much things do we produce? How much money do we have as like a country? How wealthy are our citizens? How much land is there? He starts being interested in this stuff. So here is a diagram from this time. Christopher Schreiner from 1630, recording from 1611. The recordings were in 1611, but he publishes this in 1630. Introduces the idea. Tufte would later call the principle of small multiples, where you graph out a bunch of things in like little tiny things. You graph a thing continuously over time. So here are some sunspots he was observing, and then he maps these sunspots over position over time. And these are like different, he measures them. And you can see that this is like a really early graph. Like, what are these? Why is he just writing in the middle here? Why can't I read any of it? That's kind of suck. I think it's all in Latin too, or something. But he's graphing sunspots over time. Like you can start seeing pattern. Like we're seeing the beginning of patterns here. So that's kind of cool. We also this is really fun. This is the first according to the author, the first known visual representation of statistical data. So this guy, Longren, basically said, well, we have all these people who think they know, all these astronomers who think they know how far away Toledo is from Roma based on looking at the stars, because we don't have accurate time navigation, because we haven't invented a stable timepiece yet. It's really important for the purposes of traveling, if you know the history of sail. But, and I can go into that if any of you are interested. But he wants to know how far away it is from Toledo to Roma. So he says, well, we have all these guesses. So my guess is it's in between. I just look at all these and I say, this is like right in the middle. That's probably where Roma is, because all these people were pretty smart So here. By the way, he's wrong. The point is actually here. Everyone was just real over guessing. The paper talks about why it has something to do with like the fact that they were calculating based on astronomy, like astronomical measurements to try to figure out the longitude. But this is he's basically figuring out a median here by drawing it. He's visually finding the median. Also, a milestone in the earliest known exemplar of the principle effect ordering for data display. He's ordering these guesses on a graph in order to properly display how he gets to his result, which is interesting. I find this graph fascinating, actually, just looking at it and being like, I see what he was doing. So political arithmetic, which I mentioned earlier. So Grant uses tabulations of London birth and deaths from parish records and the bills of mortality to estimate the number of men the king would be find available in the event of a war. This was kind of what he was doing demographic studies for at the time. He's like, how many people can we field in the event of war? Something that we actually do repeatedly with census data. Like, that's one of the reasons we do the census, is to know available military force. So and it's also an example of like approximation, like doing approximation, because he's using birth and death and parish records to guess the number of people available for war. Jan DeWitt in 1671 was building life tables for doing insurance and annuities. So we're starting to get into what is one of the big early uses of statistics? It's insurance. And I'm trying to remember the name for the actual science of like insurance, what they're called. Does anyone know?
You mean like actuaries?
Yes.
Yeah, actuarial science. Actuarial science. So this is the first graph. This is the first graph of a continuous distribution function. This is a math thing. So there's no real world application here, but Christian Huygens, I defined this graph in a separate paper, by the way. It's just graphing it has a continuous distribution function. He's like, look, I can graph this. And I think this was made. I think this is not actually his graph. I think this might be a computer graph, but this is he combined coordinate systems with probability theory and graphed a because he's basically doing interpolation here to graph a continuous distribution function. Just something we do all the time now. The mid 1680s saw the first bivariate plot derived from empirical data, a theoretical curve relating barometric pressures to altitude. So he's like, well, I got all this data, and I guess I'm going to, I have this data of barometric pressure and altitude, which I don't label my axes because we haven't really invented that yet. And this is what the curve between them looks like if I just kind of map all these data points. This is the same guy, by the way. This is Haley. He also did the first weather map. This is the first note. He also made the first known weather map showing prevailing winds on a map of the Earth, which is kind of interesting. So yeah, that's the 1600s. We're going to get into 1700s. Any questions? I'm going to take a quick pause to take a drink of my boba tea. All right, guess we'll keep going. So in 1700, we started collecting empirical data, and the rise of statistical theory and measurement error. We want to communicate more data visually because we start being interested in like explaining what we're learning to people who don't know our math, kind of, right? How do I explain my data to my king or someone else? Like, how do I communicate this effectively? In mapping, we get the invention of isolines and contours to express more than geographical position. So we start thinking about actually more than bivariate mapping. We start thinking about higher dimensional because we want to map more things than just a two-dimensional location. We start inventing thematic mapping where we start doing maps in different ways to communicate even more data. There's other really important advancements in this period. We have 3-color printing invented by Jacob de Blon in 1710, and lithography, invented by Elos Sennefelder in 1798. And these both really facilitate distribution. Now, granted, 1798 really puts that at the end of this period, so it doesn't really matter for this period. It matters for next period. But these are really important inventions for, like, because we have to distribute our prints, right? You know, it's one thing for me to just draw it, and it's really helpful if I can start delivering it. 3-color printing also means that I can start using colors as a way of expressing information too, which is important. So this is Edmund Halley, who is this guy, by the way. I think this is the same guy. He starts doing contours, isolines, to show contours of equal value on a coordinate grid. These are lines of magnetic declination. It's also the first example of thematic cartography, where we express more information on a map than just this. Like, this is a map to express, like, magnetism on a map. And he invented this. He was the first one to do this. He's like, what if I did this? This is interesting. These guys, Jacques Darboux and Joseph Priestley, are the first people to discretely map time, to try to, like, map time graphically. Timelines. Timelines, or chronologies, were first introduced by Jacques Darboux in the form of an annotated chart of all of history from creation on a 54-foot scroll. And this is a photo of his scroll open to the years 360 to 510. And he just made this timeline of all of history, which, you know, was only 3,000 years to him, but it was a 54-foot scroll, so that was impressive. Joseph Priestley, presumably independently, used a more convenient form, this is then a 54-foot scroll, to show a timeline chart of biography, the lifespans of 2,000 famous people. This specifically centered on 12,000 BC to 1500, 12,000 BC to 1500 AD. This specifically focuses on a specific period from 600 to 0. And this just shows how they all lived. And you can see that people are starting to be like, I want to compare the people's lives visually. Like, oh, I can just look at this and see that Xenophon lived at the same time as Denarius and Plato and Aristophanes, but Thales is just, like, way out there. And I don't have to, like, do the math with, like, the dates. I can just look at this picture here. Like, that's huge to, like, realize that you can just write that down. And now we just take it for granted because we all can do it. You know, you're like, hey, do these people have the same day? You're like, well, let me just check it out real quick. Well, that wasn't, you know, you had to do the math beforehand. This was the first use of geometric figures and cartograms to compare areas of demographic quantities. He provided another novel visual encoding for quantitative data using superimposed squares to compare the size areas of European states. This is Charles de Fourcroy. The 6 is me pasting. August F.W. Crum as well. So these are the size of European states, all kind of square mapped compared. So you can just take a look and you see, like, oh, they're bigger, get bigger, 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 which is kind of cool. Gives you a visual representation. I think, I don't actually know if they're embedded. They might not be embedded. That'd be weird if they're not, but not great at reading these really fast. There's not, like, a clear, we're still before the point of any sort of, like, standardization around how to graph things and map things. We haven't invented a language around it. We haven't invented any standardizations around it. So it's kind of hard to read some of these old ones. You have to kind of make, and also it's in French, so makes it harder. Johann Lambert introduced the ideas of curve fitting and interpolation from empirical data points. This pushes plotting to new points, though not necessarily pretty ones. That's me. I just found these graphs fairly boring. They're graphs that show the match between the curve of evaporation and the curve of hygrometer. So I guess he's doing curve fitting and interpolation, and this guy isn't. This guy isn't really curve fitting or interpolation, I guess. Yeah, I think he wasn't really. I guess he just drew a line. Well, this guy's actually trying to do some mathematical modeling between them. William Playfair is someone the author considers really important to the history of things. He's the inventor, widely considered the inventor of most graphical forms widely used today: the line graph, the bar chart, the pie chart, and the circle graph. You've heard of all these, I am sure. So we can see him doing some really bad graphs here. This is a redrawn version of Playfair's 1801 pie circle line chart comparing population and taxes in several nations. So this is the Russian Empire, and like you can see that like he's like doing some bar charts here. This is the population of the Empire Russia. I think this might be landmass. I'm not sure. He's plotting a lot of different things on the same thing. And taxes, and you notice that these are two different scales. This is population in millions and taxes in things, and then he's drawing a line between these to show the relationship, how much like the population to the taxes collected in each country. He intended to show that the slope of the line connecting the two would depict the rate of taxation directly to the eye. So you can see here that, Britain and Ireland are taxed per person way more because the tax collection is way more than the population. To be fair, he also devoted several pages of text describing how to read and understand a line graph. I don't know what his original graph looked like. This is a redrawn version, so I am not sure what the hell his original graph looked like. I could probably find it somewhere, but note, a lot of these images actually were broken in the paper. I'm going to post this link in the chat where I found I found a lot of it. All pie charts are bad graph. So I found this page, which is where I found a lot of the graphs. Some of those links are still broken because they link to like external sources, like an IBM thing. So it's not very well kept up, unfortunately, but you can Google stuff around and find stuff too. Here's another graph that Playfair did. I think that one actually looks really cool. He used 3 parallel time series. This was a later one he did. 1821 time series graphs of prices, wage, and ruling monarch over a 250-year period. And he used this to show the, I think this is the ruling monarch up here. This is the price of wheat here. And this is, I think, the wage down here. The price of wheat, weekly wages, reigning monarch over a 250-year span, and used this graph to argue that workers have become better off in more recent years by trying to show that the wages had increased faster relative to wheat. And then obviously trying to make some argument about the monarchs involved. Like there's obviously a political statement. Like, why the hell do you put the monarchs on here? Well, to kind of like be like, look, the monarchs are getting better, huh? But so be it. In 1794, Dr. Buxton patents printed coordinate paper. By the way, this is 20 years before lined note paper was thing. So graph paper predates note paper, patent-wise. This the utility of this prompt, the utility of everything, what everyone was doing. But graphing data would remain rare for another 30 years or so, mostly because we weren't collecting good enough data. We weren't collecting enough data. And the one data we were collecting, census data, was fragmentary. You have to go to like all these different people to collect it, and it wasn't publicly available. So there just wasn't a good use of graphing yet. All right, and now we're done 1700s. Pause to read through the chat. Any questions? No, all pie charts are bad graphs. I like some pie charts. Some pie charts are good at expressing things.
Only if they're charting pi itself.
Like, I would like if you wanted to show me a repo and then show me how many languages were present in that repo and do a pie chart to show the distribution. I think it's a pretty fair use pie chart. There are other graphs you can do, but
yeah.
Let's keep going. At the beginning of modern graphics, 1800, 1850, you can see that we're starting to get into smaller time periods as advancements are going to accelerate. In 1800, we have all the modern forms of statistical data display were invented. Pi, bar charts, histogram, line graphs, time series plots, contour plots, scatter plots, and so forth. These are all the basic forms of statistical data. All of them are invented in this time period. Mapping graphs from single maps to comprehensive atlases and thematic cartography. So we are kind of just done drawing a map. We no longer just draw maps. We now include things like we will now like color them in to depict country. We will do topographic lines to show elevation. We will depict economic, social, moral, medical, and physical things. We'll also start using novel forms of symbolism. I don't entirely know what he means by this, but he says it, so whatever. And people start using these in scientific papers. That's the really big one. Scientific papers start using graphs of natural and physical phenomena. It was very rare up to this point, but now we're starting to get more common as people are starting to use data. And this is also a drive to like data-driven science. We're starting to leave kind of some of our more theoretical bounds and starting to actually get into like deep empirical observation. And I think this is also tied to like the rise of statistics and our ability to like understand we're starting to deal with larger problems. As technology advances, we start to say like we can start asking things of a larger scale. Like we no longer have to look at 9 planets. We can start looking a little further. Like we can start recording more things. We can start sharing information more widely. We can start distributing. Like this guy just built all of our trigonometric tables. Like we have those now. Like we can start doing more. And so it's interesting here. You know, we start having measurement instruments that can return a number. Like we can start measuring like electricity, for example. In 1801, we have the first geological maps introduced by William Smith, setting the pattern for geological cartography or stratigraphic geology, which is probably a funny way to say things. In the 1820s, Baron Charles Dupin invented the use of continuous shading from white to black to show the distribution and degree of illiteracy in France. So, we're not using colors here, but we're using shade. He's like, well, why don't I just shade things differently to express this thing? And I can get so many variations on my shading that I can still get it in black and white. And this is perhaps the first modern style thematic statistical map. It attracted a wide attention. It was also perhaps the first application of graphics in the social realm. Because he actually went and like gave this to the people, kind of, because he was trying to make points about things. He was trying to make political points about illiteracy, in the region. So he wanted to advertise it. So you're trying to get almost to like what are they called? Infographics. We're starting to get into infographics too, where people are trying to use graphics politically. We start having publicized government data. So in 1825, the Ministry of Justice in France instituted the first centralized national system of crime reporting, collected quarterly reports from all departments. Is the Ministry of Justice, this would be post-French Revolution, right? Actually, compare this. French Revolution. Yeah, this is post-French Revolution, so this is Napoleonic. Is this Napoleonic France? I have to look this up because I don't know how this maps to history. It's post-Napoleonic France even. Okay. So we're post-Napoleonic France here. And surprising to me, don't know my time super well. So we start publicizing, we started collecting all the crime data. And in 1833, Andre Michael Guerrieri, a lawyer with a penchant for numbers, used this data along with other moral variables like literacy, donations to charity, all sorts of things that Christians would consider moral variables, to produce a seminal work on the moral statistics of France. And he published this. This, along with Quetelet, can be regarded as the foundation of modern social science. He invents social science from this, by the way. This is like the guy who invents sociology, kind of. He's like, wait a second. If I can map, what is it? He argues... all right, I didn't write it down. But he basically argues that like if we can map social situations like this, like we can make a science out of understanding society, like the same way other sciences do. And so that's where we start getting into sociology. He won this French Academy prize. He won a prize in statistics for his work. He used maps in a very solid to Dupin, who was this guy, to compare the ranking of departments on pairs, notably crime versus illiteracy, but otherwise pairwise variable comparisons were made. He used these to argue that a lack of apparent negative relation between crime and literacy. He was arguing that crime was not correlated to literacy, basically, and that all these people who were arguing that like you could reduce crime by increasing education were barking up the wrong tree. but he was also against increasing the number of jails. He just didn't really want to take a side. He's kind of arguing against both sides. We also start getting into medical statistics. In October 1831, the first case of Asiatic cholera occurred in Great Britain, and over 52,000 people died in the epidemic that occurred over the next 18 months or so. You've all heard of cholera. A lot of famous books and stuff were written about love in a time of cholera, right? The first known disease map of cholera was Robert Baker and shows the district of Leeds affected by cholera in a particularly severe 1832 outbreak. So he kind of he colored in all like, this is where cholera is. And he figured out, he was like, look, if you do all this map, you can see that cholera is primarily in the poor neighborhoods without good sewage. But he didn't really know much more than that. He looked at this map and he was like, it's connected to poverty and sewage, but I'm not sure much else. I haven't figured out the rest. This is important. We'll come back to this, by the way. Use of graphs began to be recognized in some official circles for economic and state planning, where to build railroads and canals. For here, we get into Charles Joseph Menard. And Menard did two simultaneous innovations: the use of divided and proportional width bars, so that the area had a concrete visual interpretation, and the use of divided and proportional width bars. The use of divided and proportional width bars. So he did both. This is a kind of confusing graph. Again, we have no concept of formalized. We have no formalizations around our graphing yet. Display width of each vertical bar shows the distance along the route. So the width is the distance along the route. The divided bar segments have height approximately the amount of good of various types shown by shading. So the area of each rectangular segment is proportional to the cost of transport. So I'm transporting this much material this far, and therefore that is my cost. And he developed this diagram to argue for settling differential price rates for partial versus complete runs. The arrows here show the direction that you're traveling with these goods, by the way. So yeah, another interesting graph. I actually think this one's really interesting. It's where we start getting into like graphs to make, we're really starting to get into like graphs to make political arguments. We're starting to get outside of the realm of like graphs to explain some science, and starting getting into graphs to like make political arguments. But you might have noticed that all the people we were talking about here are like French. So what were the English doing during all this time? Well, the English didn't really trust graphs. British statisticians and economists were philosophically more table inclined and looked upon graphs with suspicion up to the time of William Stanley Jevons around 1870. They say, and quote, facts relating to communities of men which are capable, statistics should be concerned with the recording of facts relating to communities of men which are capable of being expressed by numbers. They should not be, graphs suck. We don't trust drawings. Only numbers are trustworthy. That was the British view. They changed later, but we get to the 1850s to 1900s, what the author calls the golden age of statistical graphics. Another pause for me to take a drink of water. No questions? Okay. You're welcome. Huh?
You're looking good, man. Keep it up.
So, in the 1850s and 1900s, the official state statistical office were established throughout Europe in recognition of the growing importance of statistical information for planning. Gauss and Laplace start doing statistical theory. So we're getting past probability theory and into statistical theory. You all know who Gauss is, Gaussian distribution. You all probably heard of Laplace, and Laplace, and like what are they, like Laplace transforms, I think. Yeah, Laplace transforms. So they're and Guerry and Quetelet, who we mentioned previously, they came up in some stuff here. I don't remember exactly where. Menard will come up again too. Extend statistics to the social realm, provided the means to make sense of large bodies of data. What started with the age of enthusiasm for graphics ended with what we call the golden age, with many innovations in graphics and thematic cartography. So let's go to some cool stuff. We start getting to 3D. People start saying, wait, 2 dimensions isn't enough. Colors aren't enough. I want to display higher dimensionality data. So we start getting people to graphing 3 dimensions. Gustav Zuner does this, which is a it's meant to do projections onto the coordinate axis. So you see this box here in this shape. He's showing that it projects onto the coordinate axis like this, which is kind of cool. Do y'all understand that? So he's graphing 3-dimensional objects. Luigi Perozzo does this graph of a population in Sweden from 1750 to 1875 by year and age group, and designed on a stereogram. And you can see that like this actually starts to look like more modern graph. Like you look at this and you compare it with this, and you're like, oh, this is like readable and formalized. Like there is kind of some like that we have an X and Y axis. We've like properly laid, like things are like well written. We like our drawings are nice. You know, we maybe hired an artist. This whole topography thing is actually kind of cool. We get back to Menard. So, you know, this guy Menard, he's doing more stuff. He developed the use of divided circle diagrams on a map, showing both a total by area and subtotals by sectors with circles for each geographic region on the map. Later, he developed to an art form the use of flow lines on maps with width proportional to quantities of people, goods, export to show how movement and transport geographically. He was very concerned with how people were with like goods moving. That was his primary concern. But this is kind of apparently his most famous graph, which is a depiction of the fate of the armies of Napoleon and Hannibal. The graph shows the size of the army by width of the band across the map on the campaign of its outward and return runs, with the temperature on the retreat shown in the line at the bottom of the graph. So this is the army Napoleon invading and going through locations. So it's actually, this is his army by width mapped on like a geographic destination as it goes. It goes here, and then the black is the retreat, and you can just see the army shrinking and splitting off and stuff. Right? And then he shows the temperature because I guess he wanted to make a point about how temperature changed. I don't actually know how to read this temperature graph, like whether I read it this way or this way because it's too small. So I'm a little confused. I think this graph could still be better, but it's like it's infographic-y, right? You look at this and it's like infographic.
This is one of the most famous graphs ever, though. I mean, pretty impressive, you know, and visualization. You know,
1861, by the way.
Yeah, it's like I love this graph. It's just it makes it so clear and obvious the troop degradation and why Napoleon fell. You know, it's so good.
Like I said, Menard was very obsessed with transportation and movement. He was good at it, though. So, you know, this is a cool one. You know this graph? This is a famous graph. You can read my thing and it will tell you. But this is Florence Nightingale's graph of what people died from in battle. So y'all have heard of Florence Nightingale, the woman who basically invented the Red Cross and also said like, hey, what if like you like sanitize shit before you cut off people's legs? This is how she convinced people that it was a good idea. This is what she used. So she's using these to wage a political campaign for improving sanitary conditions. I think this is a really cool graph, by the way. Also, because Florence Nightingale is kind of cool herself. I don't know if you know much about her history. She's kind of cool. A little crazy, like most really driven people were, especially a really driven woman at this time. But like, she did this. She made this.
She actually invented the polar area chart. That's amazing. I had no idea.
Yep. She really invented this type of graph too. Florence Nightingale was very cool. And crazy. But cool. So remember this chart earlier, Dr. Robert Baker? So this is how they actually found the cause of cholera, by the way. Dr. John Snow produced this famous dot map showing the deaths due to cholera clustered around the Broad Street pump in London. Like, look at this. Like, I look at this and I'm like, wait a second. Why? They're all near this pump. Like, I drew the pump. Like, here are all the pumps, right? And here was everyone dying from cholera. I wonder if where all these people are getting their water. Because remember that this guy kind of this guy kind of said sewage, but like I'm not sure really. This guy's like, nah, it's this. It's just literally this. Cholera, by the way, is when you it's when you shit in your water. That's how you get it. So, but Dr. John Snow produced this graph and to understand epidemiologically what was happening. So this is huge, by the way. This graph was like huge epidemiologically. Why was it so much more impactful? Baker used a town plan of Leeds that had been divided into district. Baker. A population of 76,000 in all of Leeds. Baker mapped 1,800 cholera cases by hatching in the red with the district in which cholera had prevailed. Baker did not indicate the incidence of diseases on his map, nor was he equipped to display the rates of diseases. So he just identified what districts, but he wasn't specific enough. He also noted an association between disease and living conditions, how exceedingly disease was prevailed among those parts of town where the deficiency, often an entire want of sewage, drainage, and paving, but he was unable to connect the dots or see a geographically distributed outcome in relation to geographic factors. Snow formed the basis for modern epidemiological mapping. Like, look at this. You just see this and you're like, ah, yes, this is a good idea. Like, so. They're gonna he summarizes this section by just showing what the author thinks is the most impressive graph of the era, a tour de force graphic for determination of magnetic deviation at sea in relation to latitude and longitude without calculation, by Charles Lelambard, Director General for the geodetic measurement of altitudes throughout France. It combines many variables into a multifunction monogram using 3D juxtaposition of anamorphic maps, parallel coordinates, and hexagonal grids. I do not understand this map at all, but it does look kind of cool. And somebody probably found it very useful because it was published in a book. If anyone else understands this graphic, good for you, but I don't, and I don't really care to. It's very complicated. Francis Galton. Galton, who's here heard of Francis Galton before I keep going?
I haven't. Who's that?
Okay. So, Francis Galton is really important in the field of statistics because he invented many things such as bivariate normal distributions and the standard deviation. He was also a cousin of Charles Darwin and invented eugenics.
Oh no, that's not good.
He was a half cousin of Charles Darwin, and he is the one who created eugenics. He also, if you ever heard of nature versus nurture, that's this guy. Francis Galton was the one who coined nature versus nurture.
Oh, wow.
So if you're ever going to talk about that, just remember that it was coined by a eugenicist. So he developed ideas. He was very important in statistics. His works on correlation and regression and standard deviation, bivariate normal distribution, very well known, very important to the field. He derived a lot of it from visual interpretation of data. His insight into was largely based on visual analysis from the application of smoothing to his data. The paper does not mention his ties to the eugenics movement, which I find unfortunate given how much time the paper spends gushing over Galton. But I do think it's important to understand that a lot of Galton's decisions and like things were informed by his statistical work as well. Like, kind of like this, like, you know, we start, if you want to talk about modern statistical understanding, things like hidden variables, reinforcing existing biases and stuff like that, like how to choose your variables, like a lot of that also plays into kind of Francis Galton's more like discrete work. His theoretical work is fine, like, and kind of independent of any of his beliefs, but his like field work is more problematic, if you're curious. But he did do this really cool graph. It's a remarkable chart, shows a 2-page trellis style display, shows the observations on barometric pressure, wind direction, rain temperature from 15 days. For each day, the 3x3 grid shows a schematic maps of Europe, map pressure, wind and rain and temperature in the morning, afternoon, and evening. Wayner remarks, Galton did for collectors of weather data what Kepler did for Tycho Brahe. Like how important this graph was, how important this kind of charting was. So it is cool to look at, though. One last piece, some last pieces before we end the era. We have the creation of statistical atlases. These are official government statistics on population. And they become widespread in countries in Europe. There's an impetus to develop standards because of these. There's an impetus to develop graphical standards for the graphical interpretation of, and we have the International Statistical Congress in 1869 that and they start coming up with standards. They start recommending that all official publications be accompanied by maps and diagrams to make it more consumable to the layperson. The pinnacle of this period is state-sponsored statistical albums, undoubtedly the albums de Statistique Graphique, published annually by the French Ministry of Public Works from 1879 to 1897 under the direction of Émile Chaisson. It should be noted that almost all cases the graphical representation of this data was accompanied by numerical annotations or tables, providing precise numerical values if you wanted to dig deeper. And they had data on all sorts of stuff. There was like data, like census data. There was geographic data. There was data on like who was going to the French World Fair. There was the Parisian World Fair. There was data on like how much money theaters were making, how much money each theater in France was making on like a time-by-time basis. This was one that was in this statistical almanac. It showed the number of passengers and tons of freight shipped from Paris from the four principal train stations. Of the total leaving Paris, the amount going to each main city is shown by smaller mosaics colored according to railway lines. Of those amounts, the distribution to smaller cities is similarly shown, connected by lines along rail routes. So very cool graph, I think. If you find one and blow it up, it does look very cool. If you're interested in it, very interesting. Not many people are nowadays interested in the 1882 movement of goods across France, but if you're a historian, it's very useful.
Oh, there's an entire group of wargamers that are super into 1800s rail games. So there's a subgenre of people that like really love this stuff.
Well, great for them then. Thank you, the French Statistical Bureau. He also mentions that the among the other national statistical albums, those from the U.S. Census Bureau deserve special mention. The U.S. Statistical Atlas of the Ninth Census, under the direction of Francis A. Walker, contains 60 plates, including several novel graphical forms. The ambitious goal is to present a graphic portrait of the nation, covered a wide range of physical and human topics: geology, minerals, weather, population, ethnic origin, a bunch of other stuff. Prevalence of blindness, death, mutism, and insanity, and so forth. Here is one such graph. This is interstate migration shown by a back-to-back bar chart sorted by emigration. This is, by the way, one of the first examples of sorting. Like we start actually, this is also when one of the big things that this did was sorting the data to make it more, to make it readable. So this is sorted by emigration, emigrants, and immigrants. So you can see that a lot of people are leaving New York, but a lot of people are moving to Virginia. And nobody gives a shit about Arizona or Nevada, which is unsurprising. They both suck. But yeah, very interesting. I actually like this one a lot. I think it's very clear. I think it very much tells a story. This is not in the paper, but something I want to bring up. This is what got me interested in this paper, why I started being curious about the history of data visualization. I saw an exhibit on W.E. Du Bois' work. Specifically, it was a kind of recreation of his exhibition at the Paris World's Fair called An Exhibition of American Negroes, where he was trying to make a point about kind of why there weren't more representation of American Negroes, or Black people, in larger international communities. And he was like, and he made these graphs, and his graphs are gorgeous, by the way. W.E. Du Bois has some gorgeous graphs. Just look at this thing. This is, do you all know who W.E. Du Bois is? Out of curiosity, before I keep going.
Yeah, he's amazing. Great guy.
Yeah, he was a African American lawyer who I think founded the NAACP. No, he wasn't. He wasn't a lawyer. He was a sociologist. What did he? He did a bunch of stuff. He did. He was the founder. He was one of the founders of the NAACP. I knew that. All right, I got it wrong. He wasn't a lawyer, but he did found the NAACP. He was one of the founders of the NAACP. He was also the first black man to get a PhD from Harvard. He was the first black man to get a PhD from Harvard. He was very smart. Look at these gorgeous graphs. City and rural population. Each shows kind of where all the African Americans are living in cities compared to those in rural environments. This shows the fluctuations in property owned by African Americans in Georgia between 1870 and 1900s. And he's like, political unrest, lynching, scandal ring, rise of new industrialism, disenfranchisement, and prescriptive laws. So, very interesting graph. He doesn't mention them. I just think they're very pretty graphs, kind of emblematic of some of the work that was being done in this period of in this period of data visualization. The Age of Enthusiasm and Golden Age are drawing to a close. The French albums Statistiques Graphiques were discontinued due to their high cost of printing. Statistical Atlases appeared in Switzerland in these 2 years, but never again. There are 2 more U.S. Census albums, but they're kind of boring. They're just, they're not made with love. So we get to the 1900s to 1950s. Any questions at this point? I also just need to take a break again. Now we good? Okay, keep going. So he's like, there's 2 ways to view this period. One, there are few graphical innovations. Enthusiasm for visualization has mostly been supplanted by quantification and formal, often statistical models. So we're back to like numbers. We just want everything to be super precise. But we can also view it as a time of necessary dormancy, application, and popularization rather than one of innovation. We had all these huge innovations, but now we're like formalizing them. Now we're making sure that we're right. They're good. Graphical methods entered English textbooks, governments, commerce, and science. Sir Arthur Bowley's Elements of Statistics devoted 2 chapters just to how to diagram and graph things. Just like he's like, here's how to do a diagram. Here's how to do a graph. Here's how to like do your scales. Here's how to like, all the stuff that you should know about how to graph in like science. Giffen, an early editor of Status, also wrote a statistical textbook published posthumously in 1913. It contained an entire chapter and 13 tables, but didn't contain a single graph in the entire textbook. So probably a much more boring book. Arthur Bowley. This is his demonstration of methods of smoothing a time series graph. Bowley plotted the values of total exports from Britain and Ireland over 1855 to 1899. At issue is whether exports have been stationary in most recent years. And in this textbook, it basically he uses as an example to describe how to smooth graphs. How to smooth those time series graphs. One of the big things this time period is we're starting to use graphs as a way of actually deriving insights. Scientific insights come after the graph rather than before. We're not using the graph to show our insight. We are using the graph to derive the insight. That's one of the big things. So E.W. Maunder's butterfly diagram to study the variations in sunspots on a time, leading to the discovery that they were markedly reduced in frequency. The Hertzsprung-Russell diagram, a log-log plot of luminosity as a function of temperature for stars, used to explain the changes as the star evolves and laying the groundwork for modern stellar physics. The discovery of the atomic number by Henry Moseley, based largely on graphical analysis. Y'all, yeah, this is pretty fucking important. But yeah, he's like, wait a second. There's probably something here. Experimental comparisons of efficacy of various graphs forms were begun, so people started doing experiments on which graphs are better. A set of standards and rules for graphic presentation was finally adopted by a joint committee, 1914. A number of practical aids for graphing were developed. I don't really know what they mean by this, but apparently they were. In the latter part of this period, new ideas and methods for multidimensional data and statistics and psychology provide the impetus to look beyond the 2D plane. And now we're in the 1950s to 1975s, almost at this. So here we have John W. Tukey. Are you familiar with him? He's very, very important in modern statistics. You might know John W. Tukey because he invented the fast Fourier transform and the box plot.
That's pretty important. Wow.
Yeah. In a landmark paper, The Future of Data Analysis, he issued a call for the recognition of data analysis as a specific, legitimate branch of statistics distinct from mathematical statistics. In France, Jacques Bourtin published a monumental Sémiologie graphique. To some, this appeared to do for graphics what Mendeleev had done for the organization of chemical elements. That is, to organize the visual and perceptual elements of graphics according to features and relations in data. And also, this is really important,